we pointed you to where I have a very detailed derivation of the exergy. This is the equation, E is equal to U minus U naught, etc. And then we also have a derivation out there on the exergy balance equation. Show you the property exergy, and then derive an exergy balance equation. Last time, I believe I spent some time talking about the form of that exergy balance equation. True? It said, look, it's just like a first law of thermodynamics. You have a change in exergy, not energy, exergy, on the left-hand side of the equal sign. And then on the right-hand side, you have how it came in with the flow of heat, went out with the flow of work, or was destroyed. That's it. There's no mass. This is for a closed system. So this is the equation for the transfer of the exergy with the heat. What does inside this parenthesis? 1 minus the low temperature T naught, the dead state temperature, divided by, conceptually, the higher temperature, the temperature at which the heat is being transferred across the boundary of the system. Sometimes I'll put a TB right there. What is in that parenthesis right there? What is that? 1 minus T low over T high? Carnot efficiency. That's exactly what it is. Likewise, why is this transfer with work has a typical boundary work, and then this non-useful component of the boundary work? Why is that there? Because pushing back the atmosphere doesn't help you raise a weight in a gravitational field. Then we have the exergy destruction, and we saw that the exergy destruction is proportional to sigma. I forgot what sigma is. Entropy production or entropy generation, right? When do you have sigma greater than 0? When there are irreversibilities. What are sources of irreversibilities? Friction, heat transfer through a finite temperature difference, and flow through a restriction, flow through a pressure difference. When is sigma equal to 0? When sigma is greater than 0, you have irreversibilities. When there's no irreversibilities, it's equal to 0. It's frictionless, everything's as good as it can be, right? When is sigma less than 0? When is it negative? Never. It's impossible. You've now violated the second law of thermodynamics. What is T naught? Dead state temperature. You multiply the dead state temperature times the entropy production, you get the exergy destruction. Why is there exergy destruction? Why is there the destruction of the ability to do useful work? Irreversibilities. That's why, just irreversibilities. So we have water in a rigid tank, and it's heated with an electric resistor. So we have another tank, and it's rigid. Hey, we're getting good at rigid tanks, aren't we? And it has an electric wire coming in, and then it has a resistive element, and then electric wire going out, okay, of the tank. And the tank contains 1 kilogram of water. So we make a little note. We say, oh, the mass is 1 kilogram. And if you tend to forget things, you underline them or highlight them or something. It's water. Water, water. When you hear air, you think either it's ideal gas, you have the air tables, you hear water, what do you think of? Steam tables. You got tables for properties, especially if it's two-phase or slightly superheated. Okay? Okay. It's initially at 100 degrees C and a quality of 39.2%. So the temperature initial is 100 degrees C and the quality initial is 39.92%. And it fills a well-insulated rigid tank. Well-insulated. What do you think Q is for a well-insulated rigid tank? 0. So the water is heated by an electric resistor until the temperature of the water is 130 degrees C. Now T2 is 130 degrees C during the heating process. Determine the change in the energy of the water. What's the energy of the water? What is the change in energy of the water? Two things to struggle with when you ask the question. What symbol should I use for the answer? And then what units should I have for that answer? Then the next thing is, what is my process to get that answer? I'm going to stop, pause. I want to walk around and see if you can't get those three things nailed down on your work, your sheet of paper for part A. And if you're really good, move to part B. Okay? What symbol am I looking for the answer called the change in energy of the water? What are the expected units? And how am I going to calculate it? All right, so the change in the energy, some people said, I think I'm going to put it's the change in E, right? But then that's very general, and that would include internal, kinetic, potential energy. Some people just said, you know what, it's just a change in U because I can tell it's a rigid tank. There's no kinetic and potential energy. So I'm going to look for a change in U, cap U. What are the units on that? Kilojoules. How would I solve for the change in the internal energy of the water? How would I do it? Not really, because we don't know anything about W yet. And if you look, part B says what the amount of energy transferred by electrical work. This is WELEC in units of kilojoules. We're going to have to calculate for part B that. So if you start with the first law, you're going to say delta U is equal to Q, and then you have the minus the work out, right? But we know that electric energy in, this is my control mass, that's my system. It's enclosing the water, right? What cuts across the boundary right here and right there? Two electric wires. The electric wire, one is high voltage, one is low voltage. The current through them is the same. And so we know the electric power is the voltage difference times the current flow. And if you integrate that over the length of the time of the process, you get how much electric energy flowed in. Since that's a flow in, what I'm going to do is I'm going to say not an out, an in, put a plus there. And I'm going to say the electric in. Okay? So when I calculate the electric work, I will have redefined the direction. Yes, sir?
So basically saying it's work done to the system makes it positive.
Yes, it's a positive contribution to increasing the internal energy. Yes. And so we would get to this point and we'd say there's our first law, and I'm stuck because I don't know delta U. That was what I needed to solve for part A, and if I could solve for that, sure would make solving for part B easy, wouldn't it? So backpedal a little bit. How am I going to solve for delta U? Okay, put a diagram up. TV diagram. So you can do something like that, but let's say I put a temperature volume diagram up. It'll be very steep, and then it'll be very kick out like that, okay? And we have a line. Do you want PV or TV? Either one. Either one, right? So we know it's at 100, and it's going to end up at 130, and it starts off at this line right there. It starts off at a quality of 40%, roughly, 39.92%. I don't know exactly where it ends. Help me out, somebody else. Okay, but even this is a change in cap U, isn't it? That's what I'm looking for. So the change in cap U is equal to m times lowercase u2 minus lowercase u1. True or false? So the goal is can I get lowercase u1? Well, I have to go to the steam tables. It's water. Don't forget it's water. Sometimes people, oh, it's water. Let me go to the refrigerant table or whatever, right? Let me use PV is equal to RT because, you know, I used it before the previous problem, ideal gas equation, right? don't use that for water, especially in the dome. Believe me, I've graded enough exams. Students forget what substance they're working with, and they run off and grab whatever table and whatever equations. So it's for water. Use the steam table, and we have to fix the state. We need two independent intensive properties to fix the state. What two independent intensive properties fix state 1? Temperature and X. T1 and X1. What was X1 again? Quality at 39.92%. So I get out of the table. It's a little bit of work. Somebody was saying, look at here. Get use of F, add to it X1 times use of G minus use of F. True? Is that what you're leading me to? Does that all make sense? How do I get U2? Well, don't leave the steam tables. Stay in the steam tables somewhere. What two independent intensive properties do I know or can calculate? T2 is 130 degrees. Now I'm stuck. Okay, do me a favor. This is what you do. You make a list of every property you know out of Thermo 1, period. Start and be able to write that list quickly and all the time. Start with, I would say, P. Then go T. Then go V. Then go U. Then go H. Then go S. Now go E for Exergy. And we could continue that list. C sub V, C sub P. These are all properties, I know, but we're getting down to the ones that are probably not relevant. K, the ratio of specific heats. There's a lot of other properties. Beta, we'll get to alpha, we'll get to other properties, okay? But those are the big ones, this top of the list, right? And think, do I know the pressure at state 2? Or could I easily calculate it? No. To temperature at state 2, bingo, bingo, got one of them. Specific volume at state 2, do I know it or is it easily calculated? And you were helping me, right? Yeah, you were. So why did you say, I can get V2? Why were you saying I can get V2? Because he solved enough of these problems already, and he knows some of the patterns. And when you have a rigid tank, the volume's not going to change, and the mass isn't changing. The ratio of the volume and the mass, you conclude V2 is equal to V1 with a little logic. Rigid tank. True? All right, so what happens is you can find V2, that's equal to V1. How did you find V1? You just use the same type of equation to get U1. It's going to be V sub F at 1 plus the quality at 1 times V sub G minus V sub F. That makes sense? Thumbs up? You're following me? Now we do this. You got U1, U2 calculated. Bingo. What's going to happen is this is a funny quality because you're going to find this is exactly U sub G at 130 degrees C. It's hard to show, but guess what? The volume stayed constant, and you end up being, and that's a bad diagram, so I'm going to change it. You end up going from 1 to 2, and that's what it looks like on a TV diagram, the process. The volume has to stay constant. But somehow, this quality at state 1 is 40%, and you go to 100% quality at state 2. What it means is every time we draw these somewhat TV or PV diagrams that are fairly symmetric, we're so wrong. It is skewed and kicked way out onto the right. The real diagrams are kicked way out to the right, okay? Make sense? So, are you ready to go to part B? Yes, sir.
Didn't you use the temperature to quality, the same quality X1?
No, because the quality at 2 is 100%. It went from 40% quality to 100% quality. It's now saturated vapor. It went from a point right here to a point right there. Yes, sir.
And that's the reason for using just UGM.
Yeah, what you'll find numerically is when you find that B, that V1 is V2 is equal to V sub G at V sub G at 130 degrees C is exactly my V1. This is a made-up problem. I made it up just so it would land there. That's why I picked X to 4 significant digits. 39.92. All right? Make sense now? Guess what? You have good notes? Because this problem continues. What did we just do? Answered questions about energy. What do you think the next slide is going to ask you about this problem? Questions about entropy. So I pause. I want you to answer the question, how are you going to now change or calculate the change in the entropy of the water? How are you going to calculate the amount of entropy transfer with the electric work? And how are you going to calculate the amount of entropy production during the process? All right, so first of all, we struggle with, we want to calculate delta S, and we know the answer has to be in kilojoules per Kelvin, true or false? For the next part, the amount of entropy transfer with the electric work, something like STRANS with the work electric. You know, you make up some symbol for what you want to calculate, right? All right. An amount of entropy production during the process, sometimes S gen or sigma. This book uses sigma. Other books use S gen. That's the amount of entropy production during the process, true? Oh, I forgot. What are units on this one? Entropy transfer, kilojoules per Kelvin. Entropy production, kilojoules per Kelvin. True or false? Do you understand all that? Now, what is the method to solve for part A? Same method as the part A for the previous problem when we had to deal with changes in energy. We exploited that energy is simply a property. If I can get other properties fixed, I can evaluate at that. True? So the change in cap S is equal to M times S2 minus S1. Can I get S1? That's the entropy of water, knowing, hey, T1 and X1. Is that true? That temperature and quality fix the state. I'm able, hey, how did I do that? S of F plus quality, S of G minus S of F. True? Hey, that equation sure does look like the equation for you. It is, very similar. How about S2? S of the steam at temperature 2 and V2, where V2 is equal to V1. And guess what we're going to find? That's equal to S of G at the T2, because it's saturated vapor at state 2. S of G at state 2. So those let me calculate delta S, okay? Now, how about the amount of entropy transfer with the electric work? I'm going to give you a second to think about that and give me the answer. So who knows the answer for the part B? Anybody? Okay, can you tell me? Is it going to be negative? Is it going to be 0? Or is it going to be positive?
0.
Take a guess. Negative, 0, or positive? Do you like to vote? We'll do this. We'll vote. All those that think that the answer, this entropy transfer with the work electric, is negative, raise your hand. All those that think that's equal to 0, raise their hand. All those that think that it's positive, what you do is you look around and you say, ah. All right. Entropy can be transferred with heat. Show me any equation in the book where it shows you how entropy is transferred with work. Can entropy be transferred with work? Oh, no. The idea of entropy is a measure of molecular disorder. I know that's not perfect description, but it's close enough. Heat transfer is really disorganized energy. It's high molecular kinetic and vibrational energy modes. But work, shaft work or pushing a boundary like that, is very organized energy transfer. It has no disorder with it on the molecular level. It's all organized energy transfer. Hence, there's no entropy transfer with organized work. Got it? Answer to that one, whatever symbol you want, we had to make it up. Transfer with the work is 0. Be done with it.
So every time you see the word entropy and work together.
Now, the last one, amount of entropy production during the process. Finally, we're going to do the second law for the process. What's that equation look like? S2 minus S1. How's the entropy of the system change? It can change with bringing it in entropy with the heat, right? What was that? Q over TB if it's a constant boundary temperature, right? And then we'll have plus entropy generation. That's an N. Entropy generation. True. Was there any other? There's a closed system. There's no mass transfer. So in this system, why is this term equal to 0? It was a well-insulated tank. And so if I want to calculate the entropy production, it's equal to the same numeric value as the answer for part A. So sigma is equal to that. Boom, boom, boom. Got it?